Hello everyone, my name is Geng Yafei, and today I'm going to present my paper titled Design of a Credit Card Fraud Detection System Using Low-Res Augmented Data and Stochastic Ensemble Neural Networks. As digital payments grow rapidly, fraud detection has become a serious challenge for financial institutions. This study focuses on how to effectively handle the severe data imbalance in financial transactions using enhancement techniques. The course code is ABW508, and my supervisor is Dr. Kokaiwa. The main challenge in this research is that fraud cases are extremely rare in real-world credit card transactions, only about 0.2%, which causes traditional models to be highly biased toward normal cases and struggle to detect fraud. To solve this problem, this research combines the low-res oversampling technique with a Bayesian DNN ensemble model. By generating a large number of high-quality fraud samples, the imbalance ratio was reduced from 577 to 1 to 1.25 to 1. As a result, this research achieved impressive performance on several key metrics. F2 score reached 0.8135 and MCC was 0.7823 and AUC was 0.9712. Outperforming all baseline models, these results provide a new direction for financial institutions to deploy practical fraud detection systems. This research focuses on two score challenges. First, extreme data imbalance. In the dataset used, there are over 280,000 transactions, but only 492 are fraudulent, less than 0.2%. Such imbalance makes model easily biased towards normal classes, resulting in missed fraud cases. Second, the limitations of traditional method. They rely heavily on handcrafted feature extraction and respond poorly to complex and rapidly evolving fraud behaviors, making it hard to continuously improve detection performance. Based on these challenges, this research defines two main objectives. The first objective is to introduce the low-res oversampling method. The low-res is an advanced synthetic sampling technique that creates new fraud samples in the neighborhood of minority data using random combinations and noise injection, while preserving the original distribution. The second objective is to build a deep neural network model using a Bayesian strategy. The goal is to achieve a practical balance between precision and recall. In financial scenarios, high recall is essential, but false positives must also be well controlled. This research uses a real European credit card transaction dataset with over 280,000 records, of which 492 are fraudulent. After data cleaning and testing splitting, the training set includes 394 fraud cases. All features were standardized and reduced using PCA to improve noise and improve learning efficiency. For the oversampling stage, the low-res technique was applied. It selects k-nearest neighbors, then generates synthetic fraud samples by adding Gaussian noise and using random convex combinations. This expanded the number of fraud samples to around 180,000, greatly reducing the imbalance. For model construction, this research designed a Bayesian DNN model, which integrates multiple DNN submodels with the same structure. Each submodel has 3 layers with 128 and 64 and 32 neurons, uses the ReLU activation function, and is trained for 300 epochs. Majority voting was used to enhance the overall performance and stability. The experimental results are very encouraging. Several models were tested, including Geng DNN10, Geng DNN20, Random Forest, and XGBoost. Among them, the Geng DNN models performed the best. The Geng DNN20 model achieved a precision of 73.21%, F2 score of 0.8135, and MCC of 0.7823, demonstrating strong control over false positives. Meanwhile, Geng DNN10 had a higher recall rate of 84.69% and the highest AUC reaching 0.9782. From the confusion metric, it can be observed that Geng DNN20 successfully identified 82 fraud cases, with only 16 missed, showing good practical value. This research presents several key findings. First, the Geng DNN model achieved a great balance between precision and recall. Compared to traditional models, it shows higher robustness in handling imbalanced data. Second, the ensemble strategy greatly reduced model uncertainty, leading to more stable and accurate outputs. Third, deep learning performed excellently in recognizing complex fraud patterns, far beyond what rule-based or shallow models can achieve. Finally, Geng DNN is highly suitable for financial deployment. It improves recall while effectively controlling false positives, helping avoid customer loss and trust issues. This research offers several notable advantages in terms of methodology. First, it effectively addresses the extreme data imbalance problem, which is a major challenge in real-world fraud detection. By using the lowest oversampling technique, the minority class was greatly expanded while preserving data quality and structure. This allows the model to learn more effectively from limited fraud examples. Second, the proposed method achieves an excellent balance between precision and recall. This is especially important in financial scenarios where high recall ensures the fraudulent transactions are caught and good precision avoids too many false alarms that could affect customer experience. Third, the model demonstrated superior performance across multiple evaluation metrics, including F1, F2, MCC, and AUC. These results consistently outperform baseline models, showing the method is both effective and reliable. Lastly, the model is highly suitable for deployment in financial institutions. It is stable and capable of adapting to real-time detection environments. By integrating ensemble learning with deep neural networks, this approach balances the detection performance with practical feasibility. In summary, this research successfully combined the lowest oversampling with a Geng DNN ensemble model. This not only solved the imbalance problem, but also exceeded the targets for F1 and F2 scores, confirming the model's practical value. This research also proposes several future directions such as building dynamic and heterogeneous network architectures to enhance real-time detection and exploring the cross-domain generalization in other application fields. That's all for my presentation. Thank you for your listening.